Good morning, Internet. I am Matt Booyak, and in this video, we'll be taking another look at the 25th problem from the Project Euler problem archive. So you may recall that this problem asks us to find the index of the first Fibonacci number with over 1,000 digits. Now, in the last video, we solved this problem using a C++ program. In this video, I'm going to show you how to solve this problem using analysis alone. So let's get into it. We'll open up our problem 25 analysis file, which is currently empty. I'll also open up the analysis file from problem 2. This was a previous problem that we had solved involving Fibonacci numbers. And in particular, we used this equation here for the Fibonacci sequence. And so we're going to use that again in problem 25. You may recall that this equation depends on the constant phi, which is just the golden ratio defined as follows. And so our expression for Fibonacci numbers is just going to be phi to the n minus 1 minus phi to the n all over the square root of 5. Okay, so let's take a look at this expression here. I'm going to take this and divide it into two separate terms. We're going to have phi to the n over the square root of 5 minus 1 minus phi to the n also over the square root of 5. And what we'll notice if we try plugging in some values for n here is that this second term becomes small quite quickly. So let me just show you how that's going to work. If we pull up a calculator here and calculate phi, so that's just going to be 1 plus 5 to the 0.5 over 2. And we'll save that. And then we'll note that 1 minus phi is negative 0.618. So we'll just say note 1 minus phi is roughly equal to negative 0.618. And then we'll also note if we square this value, we get a number that's less than 0.5. In particular, it's roughly 0.382. But all we really need to note is 1 minus phi squared is less than 0.5. And so combining these two facts, we can conclude that therefore the absolute value of 1 minus phi to the n is less than 0.5 for n greater than or equal to 2. That is 1 minus phi cubed, 1 minus phi to the 4th. They're all going to be less than 0.5. And the important thing about this is that that means that this second term here is going to always be less than 0.5 for large values of n. So that means we can get our Fibonacci numbers by rounding the first term. That is, we don't even have to bother with the second term. We can just calculate the first term, round to the nearest integer, and that will give us our Fibonacci number. Okay, great. So the next thing we're going to do is consider a function f on the real numbers with f of x equals phi to the n over square root of 5. So note that this is just that, that first term up here in our capital F of n. The only reason I'm making a distinction here is that our Fibonacci sequence is only on the integers, and by considering inputs and outputs that are not integers, then that will let us use the techniques of classical analysis to help us track down our solution. And so we'll say, note capital F of n is then just equal to round f of n. That is, just take lowercase f of n and take the result and round to the nearest integer to get our answer, as I mentioned previously. So this will let us solve for an approximate answer. And we'll say, let f of a equal 10 to the 999. So a is just going to be some real number, and 10 to the 999th power is the first integer with 1,000 digits. So we'll just say, note a is some real number, and 10 to the 999 is the first integer with 1,000 digits. Okay, so now we can actually solve for a without too much difficulty. We'll just say phi to the a is, well let's see, f of a is equal to phi to the a over square root of 5, which is equal to 10 to the 999. So then taking the log base 10 of both sides, we get log of phi to the a over square root of 5 is equal to 999. You'll notice that taking log base 10 of this value just removes the base there, and we get the exponent 999. Then applying some more rules of logarithm, you get a times log of phi minus log of square root of 5 equals 999. Okay, and solving for a, we get a is equal to 999 plus log of square root of 5 divided by log of phi. Okay, so let's punch that into our calculator. We're going to get 5 to the 0.5, take the log of that, plus 999, divided by the log of phi. And so that's going to give us roughly 4,781. As you might expect, this is not an integer, and so this does not correspond to a Fibonacci number. That is, any Fibonacci number is going to have an index that is an integer, and so this is not cannot be our solution. But what we can show is that our solution must be either 4,781 or 4,782. And so why is that? It might seem intuitive that that would be correct, but we need to actually prove it. And so we'll say, note f is an exponential function, and so is always increasing. And so we'll say, also note that the ceiling of A is greater than or equal to A. And f of ceiling of A is greater than or equal to f of A, which is equal to 10 to the 999. Therefore, f, capital F of ceiling of A is equal to round of f of ceiling of A has at least 1,000 digits. And so we know that the ceiling of A is a candidate solution. At the very least, it has 1,000 digits. So then the only question that we have left to answer, what about f of floor of A? Does that have 1,000 digits? Okay, so we'll note that using similar reasoning to what we wrote up here, we'll say floor of A is less than or equal to A, and f of floor of A is less than f of A, which is equal to 10 to the 9999. So it may seem that f of floor of A can't have 1,000 digits, except it might round up. And so this means f of floor of A, actually let's do capital F of floor of A, can only have 1,000 digits if f of f of A minus f of floor of A is less than 0.5. That is, if the difference is less than 0.5, then it will round up to 10 to the 999, and then it will have 1,000 digits. Otherwise, it will not have 1,000 digits. And so this is the only question we have left to answer, is whether this difference is less than 0.5 or greater than 0.5. So we'll say, note that f of A minus, actually we'll say, note that A minus floor of A is less than 0.5. In particular, it's roughly 0.85927, but that's the exact value isn't important. All we need to know is that it's less than 0.5. Therefore, if f has a slope of at least 1 when let's see, floor of A is less than or equal to x is less than or equal to A, then f of A minus f of floor of A must be greater than 0.5. So that is, because we know that the difference in the x-axis is at least 0.5, if the slope is greater than 1, that means that the difference in the y-axis must be also greater than 0.5. Okay, so how do we determine the slope of f? Unfortunately, we're going to have to use a little bit of calculus. It's not too bad, so I hope you'll bear with me here. So again, we'll recall that f of x is equal to phi to the x divided by square root of 5. And therefore, f prime of x is just going to be equal to the natural log of phi times f of x. So this is just the rule for the derivative of an exponential function. And so, like I said, not too bad. And so we just have to show that that this is going to be greater than 1 over the relevant values. So let's take a look at this natural log of phi. So we've got our value phi here. Take the natural log, 0.481. So we'll just say note natural log of phi is roughly 0.481. And in particular, it's less than 0.5. Therefore, if f of x is greater than or equal to 3, then f prime of x will be greater than 1. And that's easy to see that. Actually, I should actually have written this the other way around. We'll say that this is greater than 0.4, and therefore, if f of x is greater than 3, then f prime of x is greater than 1. Okay, so we just need to show that f of x is greater than or equal to 3 over the relevant range. And in fact, it's quite a bit greater than 3. But let's go through the steps to prove it formally. So we'll just note that, for example, if we punch in the value 4, then we have phi to the 4th power divided by square root of 5 is going to give us 3.06. And so note that f of 4 is greater than 3. Also, both f and f prime are increasing. Therefore, f prime of x is greater than 1 for x greater than or equal to 4. And therefore, our answer is 4,782. Let me just check to make sure. Yes, 4,782. That is the, I'll just say ceiling of A, which is equal to that value there. And so if we jump back to the archive, we can check and see that that does indeed match our answer. So that will be all for this video. In the next video, we will be continuing with problem number 26.